All right then, so talking about unfeathering now. So to feather it, you pull it back, the control all the way back, and it's going to lift the lift rod, and the lift rod is going to drain off the oil from the prop, and the prop is going to go into feather all by itself because it did not have any oil to keep it from doing anything else. So centrifugal twisting force takes over and puts it into feather. So, but to unfeather, the system may use an accumulator. Doesn't have to, may use an accumulator. Accumulator, sorry about that. So an accumulator has often been described as a capacitor, an electrical storage. And you're thinking, oh, please, no, don't do that. So let me pull up some pictures of accumulators. Yay, I have a picture of accumulator. All right, so these are accumulators. And the way an accumulator works is, you know, a lot of homes have accumulators now too in the hot water system. So we can take a look at this one. So you can see that there's a rubber diaphragm in here that separates an oil side from an air side. And you can see that there's an air valve. So what you do, this is like basketball or something here, part of it. You put a big air charge on here, and then it's going to stretch this diaphragm all the way over to here like that. And so there's all this pressure right here pushing the diaphragm. But then the oil builds up and it pushes this diaphragm back this way. And so the air pressure in here really builds up, right? So now we have all this air pressure here trying to force it out. And then you can lock this down, and now you have a storage of oil pressure. And then open that up, and then this air pressure will push the oil out if you don't have any other pressure. So you can have the ball type with an air charge, or you can do the same thing with a spring or a nitrogen charge. This is just a cylindrical version of the ball version. So same thing, and there'll be a piston in here that moves back and forth. So that's an accumulator. I think, what is this, the governor lift rod? Yeah, governor lift rod over here. Just, I don't know, not the greatest picture, but when you bring it all the way back, it twists this, it lifts it up, lifts the lift rod then lifts the pilot valve lifts up, and then it just drains all the oil from the prop right out and through. Straight shot, drain it out. So there we go. So you have your accumulators and your lift rods. All right, so to unfeather, the system may use an accumulator. So an accumulator stores engine oil pressure. Actually, I want to say it doesn't store engine oil pressure per se. It's actually going to do it. We'll go with engine oil pressure. I was going to say it could, under some circumstances, actually store the governor pressure. So, and then the accumulator may be air pressure or spring loaded. May use air pressure or spring pressure. I think I have another drawing here. Let me take a look. Yeah, we'll just show this one, see what the heck. So, since I got it. There we go. So this is, I don't know, not the best picture for you guys, but we can take a look at what's going on. So under normal circumstances, I'm going to say normal is under normal operating conditions. This is why I said I really believe it's governor pressure, not engine oil pressure. It's tied into the governor line, and the governor is going to see this little ball, check ball here. I really need to zoom that in. There we go. The little check ball is down. And so governor pressure comes through here, around here, and it's going to fill up the accumulator. And then what's going to happen next is when you feather it, so you've rotated it and you put it in the feather position. So as soon as you put it in feather, it releases this ball check valve that blocks the passage. And now you have governor pressure stored inside of this right here. All right. And then I want to unfeather it. really all I'm going to do, it's going to look just like that. I bet you, bam, it sure does. So just to unfeather it, as soon as you bring it into the normal, any of the normal positions, it pushes that little that check ball valve back down, and you line up the passageways to the prop. And so the stored governor pressure just makes it past here and goes right to the prop. And now that you have governor pressure there, it's going to drive the prop over to a higher blade angle, or at least out of feather. And as soon as it gets anywhere out of feather and starts to windmill on its own, then the governor is going to, well, the engine starts running, which then runs the oil pump. When the oil pump runs the crankshaft starts running, the crankshaft is connected to the governor, and the governor gear pump starts running, and it picks up oil pressure, and it just starts running all on its own. And so that's how everything works. It's so simple. When the prop control, you know, I'm going to go back to maybe stores. I don't want to say engine oil pressure. I'm going to say governor oil pressure. I like that better. So when the prop control is placed out of feather, a ball valve in the governor, a ball valve in the governor will release oil pressure to the prop. Will release oil pressure to the prop. And the prop then starts to unfeather and spin, and then the rest of it is just sort of automatic. So props or systems without an accumulator are simply started in the feather position, with the starter. And it's pretty hard on it. And of course, as it starts to rotate, then you build up oil pressure. And as soon as you get the prop to move just a little bit into the wind and the wind starts helping, then it starts helping the starter. So it's not as bad in flight to use the starter. But it definitely is on the ground. It's pretty hard on them. All right. I'm going to have to rewrite my notes. I don't love how I did it. I kind of go back into the Hartzell steel hub, compact hub, and I talk then again about how they work, which we already did. But you know what? If I don't, this is really the feathering mechanism, so I guess I should go with it. So Hartzell, let's see. Let me think, do I want to do that? Yeah, let me see here. I know what I'm going to do. So Hartzell feathering. I'm going to go it this way. Hartzell feathering. I like that. I'm going with that. So, we'll just go with this. So Hartzell feathering. We'll go steel hub. That's what we'll do. We'll make that the I, and then steel hub. We'll talk about the steel hub. How does it work? So oil pressure, you should know this, oil pressure to decrease blade angle. And then it's going to use, this is kind of new, air pressure. I'll show you where. Air pressure to increase, I should say, and counterweights to increase blade angle. And then I'll just add that it uses latches, and well, it's actually external external latches to prevent let me see, feathering on ground, because yeah, you wouldn't want it to feather on the ground. That means it's normal shutdown. All right, and then we'll say the compact hub. The compact hub. Okay, so same thing, oil pressure to decrease blade angle. We've got, well, I'll write that just to keep things moving along nicely. Oil pressure to decrease blade angle, because you always want that in a feathering prop. Air pressure and counterweights, air pressure. It's almost the same thing. So it is, I'm just being redundant, sorry. The only difference is it has internal latches. So air pressure and counterweights to increase blade angle. And then this one has internal feathering latches. All right, so on this prop, I'm going to pull this one up. Not the best photo quality, but I still like it because, number one, it's got the lubrication fittings here and here, but it's got this air charge valve up here. And so on these propellers, it's got this big it's got a giant spinner. But I love them because the front nose cone comes off. There's a couple little screws right here, maybe 3-4 screws that come out, and you can pull off this part of the spinner. And then there's a valve right here, an air valve, just like on a car, a tire. And then there's a sticker that tells you, and I don't have a picture of the sticker, but there's a sticker that tells you what the air pressure should be based upon ambient temperature. And so you have this air charge that goes back in here that assists the spring in putting the dome backwards and bringing the blades into feather. So you lose oil pressure, and you're going to have counterweights here, plus air pressure, plus spring pressure is going to throw this thing all the way into feather. So there's really no doubt you're going into feather. I mean, with air pressure, spring pressure, and centrifugal motion here, you're going into feather, and then oil pressure to bring it out of that. And let me go back to here. So compact hub, let me talk about the oil pressure. We'll just go to maintenance. So maintenance. So some props, if it has it, some props need the air charge checked. The air charge. Let me see, air pressure is about, so PSI is about 150. So it's a lot. And considering that most shop air pressures don't reach 150, you could use a thing called a strut pump, which is an air multiplier. But I highly recommend never using shop air for this stuff, even though you can get away with it to an extent. And the reason why is shop air has moisture in it. You should be using very dry nitrogen, because when you introduce moisture into this prop, you're going to introduce corrosion. You introduce corrosion, you're going to cost somebody a lot of money, and that's going to make them not happy. So, but the pressure is going to vary. So you have to follow.
Kevin.
Yeah.
If you use nitrogen, you cannot use air then, right?
You can mix the two, I guess. I don't know why you can't. You just don't want to. course, for you in the know, could you use oxygen? Because it's readily available. Oxygen is readily available, pressurized oxygen on most airports to fill your breathing bottles. So could I use pressurized oxygen because it's at a bottle that's at 2000 PSI, I could regulate it down. Could I use that?
No, it's oxidizer.
Okay. When you mix oil and oxygen under pressure, you get an explosion. So here's kind of a joke I always say. There's only one kind of oil that you can use when it comes to oxygenated fittings. And it says it right on, boy, I wish I could find a picture of it. Let me see. I can pick one up. Let's see here. Wasting time with this. There, this one says it. Tells you right there what kind of oil you can use.
Use no oil?
No.
Well, that's NO oil. I covered it up. It says use no oil, but it's kind of a joke. There you go. You can see a little bit now. So I tell people the only kind of oil you can use is NO oil. And so call the store. You got to ask for NO oil. Somebody should do that. Somebody should call Zach up. Hey, Zach, man, I need some NO oil. What's this for? It's for an oxygen fitting. So follow the chart on the hub. If air pressure is too low, if air pressure is too low, well, you should almost be able to instinctively think about what that's going to do, because what does the air pressure do? Helps it feather, so it may not feather. It may surge or overspeed. May surge. Surge means going back and forth hunting. I have a hard time seeing why it would overspeed. Well, because I know why, because it's pulling it. It doesn't help it to go to higher pitch. So it's going down there in low pitch. Maybe, oops, what do I got here? Oh yeah, here. If air pressure is too high, may not reach full RPM, may not reach full RPM. Why? Because the air pressure is keeping it going from all the way into low pitch. And two, you may feather at shutdown. May feather at shutdown. Why? Because the prop wasn't allowed to go all the way to its low pitch stops where the feathering latches could engage. So if feathering latches can't engage, then you've got a problem. And every time you shut down, it's going to go into a feather on that position. So, all right. So really I try not to make it too complicated. All of our different kind of propellers that we've discussed here. Go back over to here. Bring this down. I want this. There we go. Thank you. So, all right. So look at everything we talked about here. Covered that. So here, sort of covered all of these propellers in one way or another, but we could really consolidate this. So the Hamilton standard is a beast of its own. And that's the Hamilton standard counterweighted prop. And that's the reason why I wrote the CW there. So it's the Hamilton standard counterweighted, almost like a two-position prop. And that is its own little animal up to itself. It just acts very different than the other ones. But then we get into, doesn't matter if it's McCauley, doesn't matter if it's steel, doesn't matter if it's compact, doesn't matter what the brand name is. If it doesn't have counterweights, then it's really going to act pretty much the same. The only thing is with McCauley here, I added a spring pressure. I probably could have added it down here too, because some of them have spring pressure. So what moves the prop to low pitch? It's the centrifugal twisting force acting on the blade. May be assisted by spring pressure, maybe not. Doesn't matter. Centrifugal twisting force. There you go. What moves it to high pitch? Oil pressure. Always, all the time, oil pressure. And then this might just confuse you, but it just what happens with the speeder spring pressure, but it's all the same. If you have an underspeed, you're always going to drain the oil to decrease the pitch. Why? Because centrifugal twisting force moves it back to low pitch and speeds it up to go back on speed. If you're at overspeed, you're always going to send oil to the prop to increase the pitch. Why? Because oil pressure moves it to high pitch. Okay, then we can lump these three together right here. The Macaulay feathering, the Hartzell steel full feathering, the compact feathering. And there is a Hartzell that doesn't have counterweights, but it has the air oil charge on it. So, but still the same thing. Even if it doesn't have counterweights, what are we gonna do? It moves prop to low pitch. Up here we had centrifugal twisting force. We're always gonna have oil pressure to low pitch. Why? Because it's on a multi-engine aircraft. And if we lose oil pressure, it's gotta go to, over here to high. So oil pressure keeps it low. Lose your oil pressure, counterweight spring pressure, counterweight spring pressure, counterweight air pressure. And this one is just air pressure and spring because it doesn't have the counterweights if you encounter that one. But it's all the same thing. Oil pressure goes to this side, centrifugal twisting force goes to this side. You come up here, oil's on this side, centrifugals on that side. So hopefully you can see you just cross it over when you add counterweights or put it on a twin. And then this column here, it's pretty much all the same. What happens in an underspeed? Well, underspeed, oil to prop to decrease pitch, oil to prop to decrease, oil to decrease, oil to decrease, right? And then over here, drain, drain, drain. So it's all the same. The only difference is the Hamilton standard because it's its own little beast. Otherwise, it's either going to be, and so now think about it, you just throw it out. If you're on a test and it says anything, it's like the Macaulay non-counterweighted. Okay, Macaulay non-counterweighted, that means it's not a twin. If it's not a twin, this is how it works. If it's not a twin, oil pressure to increase, centrifugal twisting force to decrease pitch. Got it. You can call it anything. I could, call it a Woodward prop, right? Or you throw in the word Sensenich in here. Doesn't matter what name I give it. The question is it on a single or a twin? If it's on a single, then it's non-counterweighted. If it's on a twin, it's counterweighted. If it's on a single, centrifugal twisting force goes to low pitch, oil pressure to high pitch. If it's on a twin, it's the opposite, oil pressure to low pitch, centrifugal twisting to high pitch, right? So it's just that simple. Then you get into what makes it feather, what doesn't make it feather. All of them feather the same way. Drain off the oil, boom, goes to feather. How do you get it out of feather? You either have an accumulator or you don't, right? If you have an accumulator, you just pull it out, pull the blue knob into the normal operating range and it's going to self-light off. If you don't have an accumulator, just hit the starter, all right? It's a little hard on it, but it still works and there it goes. So, so we've got all that and hopefully that, you can just lump it into one thing or another. I am going to fast forward before we talk about the next prop, and which means I need to get out of here so I can really fast forward. And we're going to watch a video that ties this in, and I forget how long this one is, but I'll find out in a minute, won't I? And it's a little bit of an old video, like most of them, but I really do like it. Maybe I'll just go to YouTube. No, go back. It hates me. Did it go to YouTube? There it is. 30 minutes.
Hi, I'm Mark Runge. Welcome to the Hartzell Service Center. I'm an aircraft maintenance technician here, and along with maintaining our corporate aircraft, I work with customers who come to the service center for propeller maintenance. Today I'm going to show you how to inspect, maintain, and service a constant speed propeller. At Hartzell Propeller, we are strongly committed to educating technical personnel in issues that affect propeller performance and safety. Keep in mind this video is not meant to be a replacement or substitute for our manuals. It is an additional source of information to be used as a general guideline. You can also find information on how to maintain metal propellers in the FAA Advisory Circulars AC 20-37D, Aircraft Metal Propeller Maintenance, and AC 4313, Aircraft Inspection, Repair, and Alterations. Our message to you is this. First, propellers are engineered, tested, and certified against rigorous FAA criteria, but they have the best chance of operating safely and reliably when they are properly maintained. Corrosion, abrasion, and general wear can eventually cause a propeller to fail. Second, it is important that you know how to do an annual inspection on a propeller. Annual inspections and overhauls are critical to propeller service life. And finally, we need your help to get this message across to the aircraft owner. Hopefully after watching this video, you will have a better understanding of what it takes to do a good propeller annual inspection and why propeller overhauls are a necessary part of maintaining an aircraft. And remember, if you ever have any questions or are in doubt, don't hesitate to call either your local prop shop or Hartzell Propeller. We have a plane scheduled to get some work done, so we'll have a good opportunity to go over these items I want to talk about. Annual inspect. Hi Sam, I see you got your cup of coffee.
Yeah, Mark. I made this appointment today because I haven't really done anything to my prop for a while, and I figured it was time I had it looked at.
Okay, have you been having any problems?
No, not really. But I read an article the other day about a guy who had a tip failure and almost lost the aircraft. The article said that by the time he got the aircraft down, the radios had jumped out of their trays and that there was severe engine mount damage.
Well, pilots are usually up to speed about their engine, whether it'll make it to TBO, but sometimes they don't think about the consequences of neglecting their propeller. You should maintain the propeller just like you do the engine. Make sure you maintain it properly, do a good annual inspection per the FARs, and follow the TBO guidelines. Since the propeller hasn't been worked on in a while, it would be best if I followed the guidelines I use to do an annual inspection. I'll do a general inspection of the prop, clean it, do a more detailed inspection. I'll dress out repairable damage to the blades and service the hub. Once that is complete, I'll do a run-up check. Do you have any questions?
No, I don't think so. I'll be back a little bit later to pick it up.
Sounds great. Are the logbooks in the plane?
Oh, thanks for reminding me. The logbooks are in the baggage compartment. See you later.
By the way, you're going to find out at the end of the video, this guy really is a Hartzell service tech. He's not an actor. I know, it's shocking. So I think it's actually kind of cool that they used a real technician to do this.
Before I begin to work on a prop, I look at the general overall condition of the propeller. Things I look for include damage to the spinner, whether the spinner is touching the blade or not, any obvious grease leaks, and the condition of the blades. After I look over the prop, I go ahead and remove the spinner. The 4 maintenance issues we will be covering are inspecting, cleaning and servicing the propeller, blade repairs, and the importance of dynamic balancing. Now let's begin a detailed inspection of the prop. The problems we will look for are corrosion, loose blades, nicks, blade damage, erosion, grease and oil leaks, cracks, and loose or missing hardware. One of the first things I look for is corrosion. Light corrosion on the blades or counterweights can be dressed out using emery cloth followed by crocus cloth to eliminate any evidence of the repair. The hub should also be checked for signs of corrosion. If you find any corrosion on the hub or have questions about the amount of corrosion you find on the blades, contact Hartzell Propeller or an authorized propeller repair station. Next, I check for loose blades. There are 4 different movements we look for: fore and aft play, in and out play, end play, and radial play. First, fore and aft play is forward and backward movement of the blade in the hub. You can check this by taking the tip of the blade between your forefinger and thumb and try to move the blade toward or away from the plane. Slight movement is acceptable if the blade returns to its original position when released. In and out play is movement of the blade toward or away from the hub. This can be checked by taking hold of the blade with one hand and pushing or pulling the blade to or away from the center of the hub. There should be no in or out play. Blade end play is lateral movement of the blade in the hub. You can check for end play by taking hold of the tip of the blade with one hand and trying to move the blade in a lateral direction in the hub. Once again, slight movement is acceptable as long as the blade returns to its original position when released. Finally, radial play is essentially pitch change movement. Acceptable movement is plus or minus 5/10 of a degree measured at a reference station. Now I check the blades for nicks or other signs of damage. Nicks are a common type of damage found on propellers, especially those operating out of unimproved strips. You can see here that there is a nick on the lead edge of this blade. We'll return to this in a moment and show how to repair this type of damage. Blade damage can include erosion of the blade surface. When paint is removed like this, it opens up the possibility of corrosion. Grease and oil leaks are another area of concern when caring for a propeller. Leakage can be an indicator of a serious problem, such as the hub being cracked or a minor problem such as a seal being damaged and needing replaced. A small amount of leakage is common on new or freshly overhauled propellers for about 10 hours or so. I want to point out here that the only type of repair to address an oil or grease leak that can be done in the field is the removal and replacement of the O-ring seal between the engine and propeller flange. A certified propeller repair station should do all other leakage repairs. It is also important to do a visual inspection for cracks in the hub. Give some extra attention to the blade retention area right around here. Cracks may be readily visible or may be indicated by grease leaking from a particular area. For example, you may see a grease stain in this area and can't tell where it is coming from. Before wiping the grease away, mark the area and then inspect it closely. After removing the stain, the grease may have seeped through a crack and made the stain. Another indication of a crack is sudden vibration. This should be a red flag, so listen to what the pilot tells you. It is very important for you to understand that if cracks are suspected, additional inspections must be done at an approved propeller repair station before further flight. As basic as it sounds, one last thing you want to check for is loose and missing hardware. This can include anything from missing lubricaps to broken safety wire and checking torque values. Well, we've talked about the main inspection points to be concerned about, and now it's time to clean the propeller. Cleaning the propeller is a straightforward process, and there are just a couple of points to keep in mind. First, do not use pressure washing equipment on the prop. There is a chance that water will be forced into the hub, leading to a corrosion problem. You want to remove any grease or oil by wiping the area with a cloth soaked in Stoddard solvent. Next, you want to wash the propeller with soap and water. You can either dry it with a towel or let it air dry. If the spinner needs attention, we recommend polishing it with an automotive type aluminum polish. Now, let's go back to that nick we found and do the repair. It is very important to know the proper techniques to dress out a nick in the blade. Nicks and gouges need to be dressed out to prevent stress risers. Stress risers can lead to cracks and failures. There are some general rules of thumb to follow depending on where the damage is. If the damage is on the leading or trail edge, You measure the depth of the damage and multiply this number by 10. In other words, you rework the area surrounding the damage 10 times the depth of the damage. If the damage is on the face or camber side, measure the depth of the damage and multiply this number by 20. Again, you will rework the area surrounding the damage 20 times the depth of the damage. Keep in mind that all blades have limits regarding their thickness, width, and length. After repair is done, the blade must still meet the required dimensional limit at a reference point on the blade. If you have a question as to what the limits are for a blade or whether a blade is repairable or not, call Hartzell or your local prop shop. To begin, you file or sand the damaged area to the dimensions we just described. The damage we are working on is 65 thousandths deep on the leading edge. Therefore, I will multiply that number by 10 and work the area accordingly. Once the area is worked out, I then polish it with emery cloth and then crocus cloth to remove any traces of filing. Next, I inspect the area with a 10 power magnifying glass and do a dye penetrant inspection to ensure that no surface defects such as cracks or file marks remain in the repaired area. I now wipe the blade with a cleaning agent such as MEK to remove any residue. Before we leave the topic of blade repair, I want to talk about repairing erosion damage. Erosion damage is typically very similar on all the blades in a propeller assembly. However, if one blade has more extensive damage, all of the blades should be sanded to replicate the repair of the most severely damaged blade. This practice is important to maintaining the balance after refinishing. The next step is critical. We cannot overemphasize the importance of treating the repaired areas to prevent corrosion. This is done by applying corrosion preventative to bare aluminum surface. Oakite 31, Chromacoat L25, or Allodyne 1201 are approved coatings. Once the corrosion preventative is applied per the manufacturer's instructions, we can apply the appropriate finish. The correct paint for a propeller can be found in the propeller owner's manual. There are a few more areas of propeller damage I want to mention. First is a foreign object strike. A foreign object strike can include anything from a small stone to a severe ground impact. It is important to take a conservative approach because there is a possibility of hidden damage. If a propeller sustains a foreign object strike, you need to inspect before further flight. You must overhaul the propeller if you find a loose blade, noticeable or suspected damage to pitch change mechanism, a bent blade, any blade diameter reduction, a bent, cracked, or failed engine shaft, or vibration during operation. If you find any of these conditions, or you suspect any of these conditions, send the prop to a propeller repair facility for a more thorough inspection. If you have a prop with a bent blade, do not straighten the blade before sending it to a prop shop. If a propeller repair station finds evidence of an attempt to straighten a bent blade, they have no way to judge the severity of the strike. Therefore, they will assume it was severe and the hub and blade will be scrapped. Let's say that a customer comes to you and says he thinks he took a lightning strike on the prop. Then an inspection is required before flight. This inspection includes a visual inspection of the propeller, spinner, and if installed, the de-ice system. The propeller can be operated for an additional 10 hours if this inspection shows that the propeller is not severely damaged and meets the requirements found in the appropriate Hartzell manuals. Unless you have access to the overhaul manuals for the blades and the standard practices manual, you will need to contact your prop shop or Hartzell product support. The important thing to remember is that regardless of the temporary inspection results, the propeller must be torn down and inspected before being returned to full service. The damage we are concerned about includes possible arcing of the parts or superheating of the components. Both of these could lead to failure. I want to briefly mention overspeed to make you aware of what it is. Overspeed occurs when the propeller RPM exceeds the maximum RPM stated in the aircraft type certificate datasheet. The total time at overspeed for a single event determines the corrective action that must be taken to ensure that no damage to the propeller has occurred. Hartzell Propeller recommends that the tachometer be calibrated every annual. If the tach is reading incorrectly, the pilot could inadvertently be overspeeding the prop and not know it. If the propeller is placarded against operating in certain ranges, the pilot could be running the prop in this range and again not know it. Let me show you a graph for the reciprocating engine overspeed limits to help you better understand what I mean. This is a graph showing reciprocating engine overspeed limits. You can see that if a prop overspeeds at 105% for 20 seconds, no corrective action is required. However, if a prop overspeeds at 114% for 20 seconds, a search inspection is required. Taking it another step further, 116% for 20 seconds requires an overhaul, and 121% for 20 seconds retires the propeller. During overspeed, we are not only concerned about the additional centrifugal forces that are generated, but some applications have sharp increases in vibratory loads at RPMs above the maximum rated for the airframe engine propeller combination. Propeller failures are normally the result of fatigue and are usually attributed to one of the following: corrosion that has gone untreated, nicks that were not dressed out or dressed out improperly, previous history of ground or foreign object strikes, operation in a placarded range or outside of the certified operating range. The inspections that I have talked about earlier may seem like common sense, and they are, but they must be performed properly and on a regular basis, per the appropriate manual. The NTSB files are full of accounts of propeller failures from corrosion, damage, or simple neglect. Some of these failures resulted in fatalities. A failed propeller may even have been on an aircraft that just came out of annual. This leads us to believe that there are aircraft with annuals signed off when there is corrosion or damage evident on the propeller. The failure of a propeller may have more dire consequences than an engine failure. If an engine fails, the pilot may have the option of gliding an aircraft to a landing spot. However, if a prop fails and throws a blade, the vibration loads placed on the aircraft can rip the engine from its mounts, rendering the aircraft uncontrollable. You need to remember that the propeller is the most highly loaded, yet most often neglected component of the aircraft. This is why the inspections we have been discussing are so important. Okay, we have finished cleaning and inspecting the propeller and made some minor repairs to the blade. Now we are ready to go ahead and service the propeller. The first thing we do is lubricate the hub. It is important that you check the appropriate manufacturer's manual to see what type of lubrication the propeller you are working on requires. This particular Hartzell model requires grease and should be greased every 100 hours or 12 months. If the propeller is brand new, you should grease it after 1 or 2 hours. This is because the centrifugal force will pack and redistribute the initial grease. Aeroshell 6 is the recommended grease in most Hartzell propellers. On aluminum hubs, each blade socket has 2 grease fittings. Remove the Zerk fittings from the side of the hub that corresponds to the blade trailing edge. Take a piece of safety wire and make sure the opening is clear. Using a manual grease gun, insert 1 ounce of grease into the Zerk fitting or until grease comes out the opening where the fitting was removed. 1 ounce of grease is about 6 pumps with a manual grease gun. It is important not to put excessive grease into the hub. If too much grease is forced into the hub, grease can be pushed into the center of the hub. This can cause an imbalanced condition and seal leakage problems. You should be aware that on older style aluminum hubs, the Zerk fittings are not located on the hub parting line. If you are servicing one of these hubs, you will need to remove the Zerk fitting from the engine side of the hub. Insert the grease into the Zerk fitting on the cylinder side of the hub. We are now ready to replace the Zerk fittings. We want to torque them per the owner's manual and replace the lubricaps. Hartzell steel hub propellers are a little different. Each blade clamp has 2 Zerk fittings. Remove one of them from each clamp and again, use wire to make sure the opening is clear. Then, use a manual grease gun, insert grease until grease comes out the open hole. On steel hubs, we don't have to worry about grease being pushed into the center of the hub. I should mention here that very old propellers had clamps with only one Zerk fitting. Should you come across one of these, loosen the Zerk without removing it entirely. Pump grease in until you see it come out around the threads of the Zerk fitting. If you are working on a propeller that uses an air charge, the air pressure needs to be checked per the manufacturer's manual. For example, this Hartzell model is checked every 100 hours or once a month, whichever comes first. The correct pressure should be listed on a label located either on the cylinder or the flat portion of the spinner under the removable spinner cap. If you cannot find the label, refer to the owner's manual for the correct pressure. If the pressure is low, nitrogen is a preferred charging medium. An operational run-up of the engine propeller is recommended any time the propeller is removed or significant propeller maintenance is performed. But before we demonstrate the run-up, I want to mention the importance of dynamic balancing a propeller. As you know, all props are statically balanced when they are new, overhauled, or had a major repair done. Dynamic balancing balances the propeller to the engine and helps reduce vibrations that can be caused by a rotating system. Dynamic balancing can also help prolong the life of the propeller, engine, airframe, and avionics. Dynamic balancing is only recommended, not required unless specified by the airframe or engine manufacturer. I'm going to go over just a few basic things about dynamic balancing. First, there should not be more than 0.9 ounces of weight in any one location. It is preferable to mount the weights on the spinner bulkhead. Many turbine bulkheads have factory-installed self-locking nut plates for this purpose. A propeller should be balanced to 0.2 IPS or lower. If this is not possible, the static balance needs to be checked. The propeller owner's manual will have more specific information on dynamic balancing. An operational
Well, it seems like a good place to stop for dinner.
Yep.